In the process of solving quadratic equations, we run across some situations that do not have solutions in the real number system. So in order to deal with this, mathematicians have developed a number system of the complex numbers that allow for solutions still to be found within these new items. With complex numbers, they come in a structure as follows. They are written as A plus BI, where A is our real portion and the BI is the imaginary portion. And together this real and imaginary work together to make the complex numbers. Now we've dealt with real numbers for quite a while, so let's start looking at what imaginary numbers look like. Imaginary numbers are based around this value I. And I, simply stated, is equal to the square root of a -1, because no number in the real plane when multiplied by itself would equal a -1. Two positives make a positive and two negatives make a positive as well. So if we're asked to simplify a square root, such as the square root of -9, well, this is the square root of 9 times the square root of -1. Square root of 9 is 3, square root of -1 is I. This allows us to work with having solutions in items with quadratic equation or quadratic formula that inside of the discriminant would come out with a negative value. These would not show up as actual crossings of the x-axis, but they do allow other applications to happen in mathematics and science. So as we go through, let's try simplifying a couple of these such numbers. Let's find the square root of -18 and the square root of a -75. The square root of -18 is going to be the square root of 18 times the square root of -1. Square root of 18 is square root of 9 times the square root of 2. This is still being multiplied by the square root of -1. 9 gives us 3. -1 gives us I. Square root of 2 we cannot deal with, so we end up with 3I root 2. Square root of a -75 will break down similarly. We have the square root of 75 and the square root of -1, which this is square root of 25 times the square root of 3 times the square root of -1. We have 5I root 3. So how can we visualize these and see what they look like in comparison to real numbers? Let's take a look at that. In order to visualize, we have to come up with what's called the complex plane. Now the complex plane looks an awful lot like the real plane that we work with of XY graphs, but in this case our x-axis acts as the real axis. So real numbers get plotted this way, and the y-axis is our imaginary. So if we have a number, a complex number, such as 4 plus 3i, this means we move 4 on the reals, so 1, 2, 3, and 4, and 3 on the imaginary, 1, 2, and 3, and we end up with a plot here. Now you might be asked what the absolute value of that is. It's simply asking for a distance formula from the origin. So distance formula, we had a change of 4 in our x-axis, and we square that. We had a change of 3, our real axis, we have a change of 3 in our imaginary axis. We square that, we add them together and take the square root. So square root of 16 plus 9, which is the square root of 25, which equals 5. Let's try another one. Let's use the value -2 plus 6i. So we go 2 to the left and 6 up. We end up here. Now our absolute value of this is going to be 2 squared plus 6 squared, square root, that's 4 plus 36, square root of 40, which is 2 square root 10 is the magnitude here. So as we go through and build on these ideas, we can keep adding more and more items, but it's just a matter of plotting and finding the distance formula. With the complex numbers, something else that we can begin doing is our basic mathematical operations. So let's begin there. First mathematical operations we would have are addition and subtraction. Now with addition or subtraction, it is a matter of distributive property and combining like terms. So here I have the complex number 6 plus 3i, and I'm adding 8 minus 5i. So since I'm adding, the parentheses really do not hold a lot of value. I'm going to drop them. We have 6 plus 3i plus 8 minus 5i. And I'm now going to use the commutative property to put my like terms together. That gives me 6 plus 8 plus 3i minus 5i. Now I'm going to combine my like terms. 6 plus 8 gives me 14, and 3i minus 5i is a negative 2i. So my overall value of this is 14 minus 2i. Now in subtraction, we do have a distributive property to worry about. We're going to take this negative sign and distribute it to our second complex number. So we end up with 2 plus 5i minus 9 minus 3i. Using commutative property, I'm going to rearrange these items so that I have like terms together. I end up with 2 minus 9 plus 5i minus 3i. Now again, combining my like terms, 2 minus 9 is a negative 7, and 5i minus 3i is a positive 2i. So my final answer is negative 7 plus 2i. Adding and subtracting, just keep your signs straight, combine like terms. The imaginary part and the real parts are different, so we cannot combine them, and we end up with a two-part answer. Now let's take a look at our next mathematical operation, multiplication. In multiplication, we really run across the first major changes between the complex numbers, or the imaginary portion of complex numbers, and the real number world. Let's start with a scalar multiplier. So if I have just a 7 sitting outside of a complex number, I distribute that item. So I have 7 times 1 minus 7 times 4i. I get 7 minus 28i. No difference here. One thing to bear in mind as we go through this is that I has a value of the square root of negative 1. So if I have I squared, then I have the square root of negative 1 squared, which is simply a negative 1. As we go through multiplying two complex numbers by each other, this will have more effect. So 9 plus 2i times 5 minus 3i, we are simply going to FOIL this as if it were any other binomial. 9 times 5 gives 45. 9 times negative 3i is negative 27i. 2i times 5 is 10i. And then 2i times negative 3i is negative 6i squared. But bear in mind, this I squared is actually a negative 1 multiplier. So that allows me to simplify 45. Let's take our negative 27i and our positive 10i and get a negative 17i. Then I have negative 6 times negative 1, which I am simply going to get rid of this negative 1 and multiply them together so I have a plus 6. Now 45 plus 6 is 51, so I have 51 minus 17i as my final answer. Let's do another one. Now this last one is going to be a little different as well, but let's walk through it. 2 times 2 gives me 4. 2 times negative 3i is a negative 6i. 3i times 2 is a positive 6i. And 3i times negative 3i is a negative 9i squared. Again, we're going to take this I squared portion and replace it with a negative 1 multiplier. This will in turn give me 4 minus 6i plus 6i plus 9. Now as I go to simplify this, the negative 6i and positive 6i add up to be 0. That leaves me 4 plus 9, which is 13. Now these two numbers, 2 plus 3i and 2 minus 3i, when we multiply them together give us a number that is strictly in the real number system. These numbers are called complex conjugates. And they allow us to move numbers from being in the imaginary or the complex realm into the real number set. And the purpose of that is that when we go through with our last mathematical operation of division, we are not permitted to leave imaginary numbers in our denominator. So we have to have a way of getting rid of them. Let's take a look at two examples. In our first example here, we have 4 plus 2i being divided by 5i. Now, in division, again, we cannot have imaginary numbers in our denominators. And in order to get rid of it, we have to be able to multiply this by the number 1 in such a way that it gets rid of our imaginary number. So the number 1 is simply anything divided by itself. In this case, all I have to do is get rid of that I, because all I have is the imaginary portion down there. I will multiply this fraction by I divided by I, which is the number 1. And then I'm going to distribute this over different pieces. So I have 4i plus 2i squared divided by 5i squared. Now each of these I squareds can be replaced with a -1 multiplier, and I end up with a -2 plus 4i divided by a -5. Now if I'd like, I could also express this without the negatives. I would have 2 minus 4i divided by 5 by factoring out -1 from both numerator and denominator. You can see I now have a number that is strictly real in my denominator, but does have an equivalent value to the original. If you have something a little bit more complicated, where you have a complex number, not just an imaginary in the denominator, we have to multiply this by the number 1 in the form of the complex conjugate of the numerator. So I had 5 minus I as my denominator, so I have to multiply this by 5 plus I, both numerator and denominator. Now going through and foiling this out, I receive this information. I can then replace both of these I squareds with -1 multipliers. And start combining like terms. I would get 9, oh sorry, let me go through and correct that. I have 10 and -7 giving me 3. 2 plus 35, 2i and 35i is 37i. In my denominator, this plus 5i and minus 5i add to nothing. 25 plus a -1 gives me a new denominator of 26. And here is my equivalent simplification of that complex number. So a lot going on here, a lot of new rules that came into effect, but based off the same principles and ideas that we had to begin with real numbers. So make sure you have good notes and are able to work with these items, and be ready to move forward into other parts of Algebra 2.